then. Thank you all for being here, of course. I'm excited to share this work with you because, yeah, it's definitely been over the past few years, and we're sort of nearing the finish line. So it's exciting to be able to share this information and sort of give you ideas of what it'll look like when you can access it. So to get started, just kind of an overview of everything that I'm going to talk about today. I've kind of sectioned it out, so each of these are kind of thematic, and you may be more interested in one or the other. So I just wanted to give you a sort of preview of what to look out for. The first section is looking at really just how the computer vision model was made and what that process looked like, how we validated it, all of that. The next section goes into now that, as we're looking forward to transferring data over to the Natural Heritage Program, kind of what that access will look like and what the IMAP Invasive integration looks like, so you know what to expect. And then finally, the third section is really an application of the data, in kind of a scientific statistical analysis sort of sense, where we were looking at roadside characteristics, kind of analyzing some of those with this data. And I'll note that this project, we had 5 target species. So a lot of the things that we did and my analyses were focused on the first 2, namely Phragmites, Australis, so the common reed, and knotweed, so the knotweed complex, both Japanese, Bohemian, and giant. And then there's these 3 other species that we've added. So we have a model for all of these. In the middle there, tree of heaven, the infamous host for spotted lanternfly. So it's pretty timely to get this model out. Wild parsnip there, next on the right, and then all the way to the right, purple loosestrife. So we have all of these 5 species that we've developed this model for. First, I wanted to go into a little bit of background, just about the rationale for this project and what we set out to do. So as most of you are probably familiar with, invasive plants are an expensive problem. They cause billions worth of losses across the US, and there's a lot, a lot also spent on controlling them. And then globally, there's every year an increase in damages from all invasive species, and that's kind of outpacing the increase in management costs. So looking at what we have now, it's important to find kind of comprehensive ways to identify and monitor invasive plants. So currently, ongoing monitoring requires methods that have varying limitations. Professionals can go out into the field and, we can get very high quality data, but it's expensive and time intense, especially if we're trying to do this at large scales. Aerial or space, satellite remote sensing is either expensive for the application you need, or it's of insufficient spatial or spectral resolution for emerging detection, so newer presences at smaller scales. And then community science, of course, all community scientists are super great. We're happy to have them. There's just heterogeneous coverage, with where they're located and where training occurs. So there's that heterogeneous coverage of geography and skill. So we're looking at it as another method to augment these existing methods using computer vision and roadside imagery to really just strengthen our existing capacities and kind of fill in some of those gaps that we have. So our goals with this project were to couple artificial intelligence and Street View to identify locations of invasive plants in order to do several things. First of all, we want to reduce human survey time dramatically. We want to inform management about presence at large scales, answer some ecological questions with this data, and then also provide it in an accessible and kind of actionable format to managers, scientists, and the public. So now that I've gone into all of that, I will go into the model overview itself to give a little bit of background on the data that we're using and the approach and how that process went. So Street View is one of many roadside imagery platforms. It's owned by Google, but really it does represent a novel form of data. And it's been around since 2007 and is increasing every year in coverage. And as of a few years ago, there was about 10 million miles of coverage globally. So there really is a lot of potential for this kind of application, especially with invasive plant assessment. So in combining computer vision and Google Street View, I'll give you a sense of what I mean when I say computer vision, right? So there are all these different kind of technologies that build on each other, from simple input output, you click a button, there's code that says do this thing, all the way up through reasoning with regression, learning kind of features, and then there's artificial intelligence, which is the realm that we're talking about here, where computer vision is one of the sort of application areas. And it's primarily concerned with using computers to perform image recognition or object recognition tasks. And Google Street View and computer vision have had uses either together or separately before. So they've been used for plant surveys, they've been used for insect distribution, urban tree inventories, estimating demographics, a lot of different things. But computer vision for invasive plant identification is new. So how this process worked is there really wasn't iterative development. So there was a lot of annotating of boxes. So that's what those kind of lime green squares are. So there's box annotation in the Google Street View kind of roadside panoramas. And if target species was not present, that would be marked in the image. So we did this for, thousands of panoramas. But across the way, we came up with a few issues. One of the kind of funniest was that earlier versions of the model were flagging a bunch of vineyards across the state and all the cornfields as knotweed and Phragmites respectively. So we put in work to add in hard negatives of those confusing species to give those hard examples of what the computer should not be looking for. Another interesting issue that we came across was this idea of kind of the lack of context. So essentially, the computer vision model is just sort of looking for patterns in a sense. And if there's a part of an image, that's way up in a tree, but it looks like knotweed, as the model might think, it's not taking that context into account. So that was something else that we had to add into the model. Ultimately, like I said, there were thousands of panoramas spread across New York State that we used, and we kind of split this into a training and testing paradigm. So all of those blue dots are the ones where we had panoramas with our training data set of either there's labeled as no species or 1 to up to the 5 species with boxes. So with all of that training data, the model could then learn those specific features, of plants during that training phase, and then run through. And ultimately, all of those images are then split up into a bunch of different chips with some of the extraneous information, the sky, the road, there's never going to be a plant there, that is kind of cut out. So then all of those chips are then individually looked at by the model, so it can review those. And then it'll flag what it finds, and we can evaluate the accuracy of those predicted results. So we did a bunch of iterative development to kind of try to optimize these models. And then once we were happy based on our metrics, we were able to then apply it to new areas. So every time that happens, we give it new panoramas, and then the model essentially looks at all those chips, identifies where it thinks, quote unquote, the species is by assigning a score. And those scores are visualized in red there as a heat map. And then all of those are sort of summed up together, and you get an ultimate probability that the model assigns to the image for having a particular species. But one important thing with this probability is that it shouldn't be just used as is. You want to do some thresholding based on desired performance. So you want to pick everything at or above some number of probability to pick as your quote unquote positive, what you're considering a presence. So the difference here is that there are, you can have a bunch of thresholds, but for a couple of examples of just say a quote unquote high threshold versus a low threshold, all of those gray circles are undetected true presences. So they're plants that aren't being picked up. A red triangle would be a plant that is falsely predicted as being present. And then the green is one that's correctly predicted. So if you compare a high and a low threshold scenario, you can see that the high threshold, you're getting fewer of those false predicted presences. So you're getting fewer errors in that sense, but you're not picking up as many actual presences that are out there. So the model is less sensitive than if you were to use a low threshold. You would see more of the species that's out there, you would capture more of it, but you would have a higher amount of errors along with that. And I always think about it as like if you're taking a picture with your camera in a dark room, it's going to be a grainy photo. It's noisy because there's not a lot of light there. So once we did that, thresholded at a pretty low threshold just to see what the sort of highest error rate performance would be, we looked at a bunch of different representative sampling zones across the Finger Lakes and Adirondack prisms. And we had a bunch of help with community scientists as well as RET researchers. So did a whole on-screen and then field validation campaign to sort of quantify how the model was performing in these areas where it hadn't previously seen. And ultimately, there were three kind of key takeaways. The one that was the performance across the state is consistent, so we can be confident that applying it to a bunch of different areas across the state is going to yield similar performance. The next thing is that the model captures the vast majority of presences. So at this most sensitive level, the false negative rates, so the misses were at pretty low percentage. And then the final kind of takeaway from this analysis was that on-screen validation is effective, it is sufficient because the true positive rates between the field validation and on-screen had a high agreement. And then whenever there was disagreement, it was just due to mowing most of the time. One of the applications that we wanted to look at with this data was doing a gap analysis. So as of right now, we did it for one county as a sort of test. We plan to expand this to the rest of the state and offer this as a layer at 2 different resolutions. But ultimately, the takeaway from this is that computer vision is greatly increasing our knowledge of presence in both number and across space. On the order of thousands or hundreds to thousands of records in a county. Okay, now I will get into what this data access looks like and kind of how it'll be integrated to IMAP in the near future. So the goals here were to create and share a framework that integrated these AI model predictions into monitoring workflows, and then also locate priority areas for validation and or control efforts. So I'll get into a few things here, namely the layers, different dimensions of the prioritization, and then what the workflow and validation looks like, as well as a demo of what these interfaces look like with some example data. So broadly speaking, there were several external data sets that were used and pulled through some analyses that ultimately resulted in several different products to show model predicted absences, model predicted presences, what the priority that we're assigning to these predictions is, and then also where there are priority areas. So when I say prioritization, again, broadly speaking, and I'm happy to answer any questions on this later because there's definitely a more detailed methodology behind this, but broadly speaking, there's these 4 levels of verification and or control importance based on at local scales, early detection, and kind of spatial prioritization. Obviously, some of these species are very widespread across the state, but at local scales and kind of in that asset-based protection phase, this was the idea to help with prioritization of verification and really help with that review process. So there's these 2 dimensions here. There's whether something is considered emerging or not, and then whether something, whether a specific location is a high spatial priority or not. And like I said, there's more detailed methodology. Happy to talk about it later. Once all of those data products are prepped and put into place, we then can go through the process of the dashboards and that verification process. So I will get into that now. I'm going to stop sharing just for a second as I switch over to those dashboards for you. Okay. So you have to log in with your IMAP credentials to see any of the non-public layers, of course. So here we have all of those kind of orange lines are where at this threshold, the model did not pick up particular species that were filtered on. Right now, we're filtered on the knotweed complex. And then all of these blue and red points are the varying priority levels, which are summed up on the left side there. So you can see those different priorities of verification. And there's an option too to filter by basically the duplicate distance between existing IMAP records, so that if you're interested in larger scales, you can to scale that and sort of filter out where existing that to select these locations that are farther away from existing known presences. And then of course there's also the model threshold, those various filters there, the species and PRISM geography filters. So that's the manager interface. There's a second interface that's more targeted towards the verification process and sort of some gamification of this idea as well. So I'm just going to sign in again. It's taking its time. Okay. So then there are all of these different grid cells, which were defined as high priority for various criteria. And then as you zoom in farther, there are these different predicted presences. And in this case, I think, yeah, we're on Phragmites. So in any of these, there are grid cells that can be signed up, links to a form with that auto-filled, and sign up to do that, stake your claim, and then you can look at individual specific panoramas, open that Google Street View panorama, verify it, view around. Nothing quite here, but that would be expected. Again, this current data set's at a pretty low threshold, so you would expect a pretty high false positive rate. On the left side here, there are the different kind of gamified elements and contributors there to this project. This is running on the verification from community scientists that helped us, but ultimately it would be running from individuals that are doing verification in the longer term. Okay, so those are those two interfaces. I'm going to switch back to the presentation. Okay. So we're hoping that, so the layers and handouts for how to access and use these will be available from the New York Natural Heritage Program. We're hoping to get those to them by September, ideally earlier, but just to give you a sort of sense of when you might be able to expect things after that. And ultimately, this means that any of the records that are submitted through the kind of aid of this system will roll into the familiar IMAP Invasives database and have the same confirmation process by verified confirmers. And then any email alerts will go out as per the usual. So along with this, really these interfaces are here to strengthen existing capacity, facilitate finding new predictions, and enable accessible community science to anyone with internet connectivity. And this whole kind of process can be expanded to other target species. Now, of course, there are a couple of limitations with that to consider. Namely, we went through thousands of panoramas. You want about 1,000 unique panoramas for each species to have a really well-performing model. But some of our models have on the orders of hundreds, and they're still useful. But that's just something to consider. And then also the technical knowledge of how to do this process, and then having capable hardware for computationally efficient, time-wise processing. Those are two things to think about with expanding these to other species or geographies in the future. The final section that I'll cover quickly is the roadside analysis component. So the idea here was to look at culvert presence and characteristics as predictors of plant presence, and then also identify effects of roadsides, traffic, and adjacent land cover. So the sites that we picked varied across 37 counties in New York, and these are all at culverts that were built in 2007 or later. So after there would be street view imagery present. And then we took a buffer and a transect approach. So the one was kind of just a 1 kilometer buffer looking at all the roads. And then the other approach was this transect approach from the culvert. So for that transect approach, ultimately there was, looking at defined intervals across the intersecting road, and then joining a bunch of data to each of those points to get site-specific characteristics, model predictions, and then road characteristics. And ultimately, we found that there were significant relationships for both Phragmites and the knotweed complex. They were more marked for Phragmites, namely that we found that there were many more near ramps, which is interesting, but not entirely unexpected, because there are these kind of wet depressions that can be targeted. And then there's somewhat more on primary roads, and then fewer on tertiary and secondary. For the knotweed complex, like I said, results were a little less strong, but they were still significant. So there were somewhat fewer on primary roads and then more on secondary roads, which could be due to shading and potentially competition. For the culvert piece with the transects themselves, we're looking at over 8,500 panoramas in those different buffers. And we found that traffic volume is increasing the likelihood that you would come across Phragmites, and the mechanism behind that is pretty well established with seed dispersal and that how that is impacted by traffic. Then there's also that forest area and then distance from the culvert decrease the likelihood of finding Phragmites, which for the forest is related to shade intolerance, and then the culvert piece is a little bit more interesting. So I'm going to get into that in a second. But ultimately, at about 1 kilometer away from the culvert, you'd be about 40% as likely to find Phragmites. So for the conclusions and future work, kind of looking forward, culvert presence we did find is indicative of Phragmites presence, which may not be surprising since they are wet kind of depressional areas. But these could be targeted management sites, because using results from this study, as well as other studies that are out there, there's this sort of nexus between linear roadside network habitat and then riparian habitat as well. So those could be good areas to target, especially if you're in a specific watershed where you have assets or created or restoration wetlands that you want to protect. But I will say the important nuance with this is that there isn't evidence to indicate that culvert construction itself is responsible, either from bringing in plant material that is then establishing or by creating openings. There wasn't evidence in our analysis to suggest that. As future studies go on, there's additional things that could be considered to help kind of make it a little bit more robust of an analysis. Finally, I would like to acknowledge all of the people who have done a lot of work on this project and have helped immensely. All of the RIT staff and faculty that helped on this, the Natural Heritage Program staff for all of their help with the iterative development of this and their support. All of those that helped with the annotation process, and then also community science volunteers, etc. So, and of course the DEC for funding this project. Thank you. And then yes, the questions and comments section, although I know we are low on time, so apologies about that. But you can also feel free to direct any questions to me afterwards at LTM4654@rit.edu. Okay, thank you.